So now we're talking about reflections, and I know you have done reflections before in middle school, but now we're going to connect it to the coordinate plane, and we'll do a little bit more complicated and algebraic analysis of it. All right, so by definition, a reflection in a line M, so we're talking about line M, maps every point P in the plane to point P prime, so that for each point, one of the following properties is true. Okay, so if P is not on the line M, so we're talking about this diagram right here, then M is the perpendicular bisector of P prime. So if I have P and this is its image, if I connect those two, then M should be perpendicular bisector. So what does that mean? In order to find that image, I have to draw a line that's perpendicular and then measure this distance to the line of reflection to be the same as this distance to the line of reflection to that image. Okay, now if P is actually on the line of reflection, then P prime is the same thing as P. Please make sure to write that in your guided notes. So you should be filling in this part and then this part. Okay, so now take out a ruler and you'll want to construct these lines of reflection and these perpendicular lines that we were just talking about. So we're going to reflect this triangle and reflect this parallelogram. Now remember, we said that I have to first have that perpendicular line. Okay, so here's my perpendicular line, and going from A to that line of reflection, I have to have that same distance on the other side. So that's where A prime would be. So now if I do that again for B, and on your sheet it's a little more apparent, but on mine it's kind of harder to see. But here's my perpendicular. It doesn't quite look perpendicular. I'm going to adjust this a little bit. So it almost looks like the same on mine, but on yours it'll be a little bit more apparent. All right, so if I do that, then again I'm measuring the distance from B to that line of reflection, and then measuring that same distance on the other side. So B prime would be there. And then if I do that again with C, I'm going to measure the distance from C to that line of reflection, and then that's going to be the same on the other side. So I would put C prime there. So if I connect all my prime points, that blue triangle would be the reflection over that line. Okay, hopefully yours looks very similar when you did yours. If you need to pause the video to do that, then please do so. And then again, we have the parallelogram. So I'm going to draw those perpendicular lines. This one's a little bit easier because both dots up here are on the same perpendicular line. So here I'm just measuring that distance, and then that distance. So those are my 2 points there. And then this distance. And I'm kind of estimating. You have a ruler, so you can be a little bit more exact. Okay, so there you go. We've reflected over the line, and that's probably something you're very familiar with. Point reflection, though, I don't know if you've learned this or not, but when we have point reflection, A prime is the reflection of point A across point P. Let me move this down. If, and only if, P is the midpoint of segment A prime. Okay, so if point A and point P are the same point, then A is its own reflection. And you guys don't have any points, so let's draw some points there, or label some points rather. And then I'm going to reflect over P. We'll call this P. So again, take out your ruler, and I'm going to connect A to P, and I'm going to extend it. I need to make sure that I'm going to go as far from A to P on the other side here. So it's going to be almost like doubling that length. Okay, so from A to P, let's say like if I measured mine, maybe it's, I don't know, like 1.4 centimeters. All right, then I would want to make sure that this is 1.4 centimeters. Okay, very similar to when we did a dilation of a -1. All right, and then we're going to do C. So I would make sure that I get C there, C prime, and then B has to go really far. This one's off just a hair. All right, so then now I just have to measure that distance again. So BP has to be the same as B prime P. All right, so I have all of my prime points. And then that looks like that. So I know this should look very familiar. Here, I'll put the A prime up here. So this should look like I said, that dilation that was a scale factor of -1. And remember, we said that also looks like a 180 degrees rotation. So that's what point reflection does. So all of these, have you noticed that the triangles and the quadrilaterals have stayed the same size and shape? So that means that reflection is an isometry. And then let's talk about some very specific reflections, because these are more common. If I reflect over the x-axis, and let me prove this to you so that we understand why that's true. So let's say I take a point, I'm going to do 3, 2. If I reflect that over the x-axis, then if I draw the perpendicular, I see that that's 2 units away, so I'm going to count 2 units away. And where do I end up? I'm going to end up at 3, -2. So the only thing that changed was the y-coordinates, and the x-coordinates stayed exactly the same. So that's why we have A, comma, -b. If I start with any point, A, B, then I'm going to end up with A, comma, -b. So now let's do the same coordinates over the y-axis. So if I count perpendicular to the y-axis, that's 3 units. And then 3 units over there would be this coordinate. That coordinate is -3, 2. So notice now the x-coordinate is changing, but the y-coordinate is staying the same. Now I'm going to erase those, and now we're going to do the line y equals x. So remember that y equals x goes through the origin and has a slope of 1. Okay, so if I draw my perpendicular, it's not very far, and then right across from it would be there. So this is the coordinate 2, 3. So you notice that the x and y coordinates switch places. And then if I do the equation y equals -x, so remember that's going to go through 0, 0, but have a slope of -1. So if I count from there, this is 1, 2.5, and then 2.5 would end up over here. So that would be the coordinates -2, -3. So you see how we're swapping and doing the opposite signs. All right, so that's our rules for those most common kinds of reflections. Now let's do a reflection over some random line. Okay, so we're going to have point A at 5, -3. And we're reflecting over the line y equals 2x plus 1. Remember, that's going to be a y-intercept of 1, and then up 2 over 1 for your slope. Go ahead and draw that on your guided notes so that you have a visual there. All right, so first thing we're going to do is we're going to find an equation for the perpendicular line. Isn't that what we've been doing when we reflect? We always say, okay, we're going to draw a perpendicular line. And it's hard to estimate this one because the line is not really nice and even like the other ones were. So that's why we're going to do this algebraically. All right, so to find the perpendicular equation of the perpendicular line, I need to find the perpendicular slope, which would be the opposite reciprocal. And then we're using the coordinate 5, -3. I know that A will be on that line. So if I do that, I'm going to plug in my M, my X coordinate, and my Y coordinate, distribute that. And then combine those like terms. So this is going to end up being y equals -1/2 x minus 1/2. Okay, so you can pause if you need to slow down on that. I'm going to move on. So now that we have that perpendicular line, that equation, then we're going to find the intersection point. So where does that happen? So if I were to graph -1/2, so that would be here, and then down 1/2/1, so. Okay, so it looks like this. So I want to see where is this line intersecting this line. Okay, so if we want to find an intersection point, we're just going to set the equations of those two lines equal to one another. So we already have those equations, so let's set them equal to one another. So I'm going to have 2x plus 1 equals -1/2 x minus 1/2. So I'm going to add the 1/2 over. That'll be 2.5x equals -1.5. So then that's going to give me x equals -0.6. So that's the x coordinate. And then if I plug in the x to either equation, you should get y equals -0.2. Okay, so that's my point of intersection. So that's where this point is. Okay, so -0.6, -0.2. All right, and that looks about right. Remember, I was estimating mine. All right, so let's write that as a coordinate. So now, we know that the distance from A to that point of intersection, maybe let's call that point P. So we know AP has to be the same distance from P to A prime. All right, so let's set this as the midpoint. All right, so remember, if we do the midpoint formula, that's the one that says x1 plus x2 over 2, and then y1 plus y2 over 2. This gives me the x coordinate of the midpoint, and this gives me the y coordinate of the midpoint. So since I already have this and this, I'm going to set each of those equations equal to that answer that we just got. And I'm using, again, A as my 1 point. This is the 5, -3. So that's going to be my x1, y1. So let's do it. All right, so I'm going to have x1 is 5. Don't know what x2 is. That's what we're trying to find. And we know that that should equal -0.6. For the y coordinate, my y1 is -3. And I have my y2, I'm trying to find that. And that should be equal to -0.2. All right, so let's solve, multiply both sides by 2, and then subtract the 5. And I'm getting x2 is -6.2. If I do the same thing with the y coordinates, multiply both sides by 2, and then add the 3, I get 2.6. So I know that my A prime is going to be -6.2, comma 2.6. If I were to estimate where that is on this graph, -6.2, oh, I'm off my graph, and then at +2.6, I'm going to be like over here. Okay, and that looks about right, doesn't it? All right, but you see how it'd be very difficult to eyeball that or to try to do some of our previous visual ways of finding the endpoint of the midpoint segment. Okay, so I want you to do the back of your guided notes, and then you can start your bookwork.